So if you know the transfer function, as I mentioned, you can find out the stability of the system. That's what we're going to do in chapter number 6. You can find out other characteristics of the control system. You can design the control system actually based on the transfer function. And you can also find the output if you know the transfer function and if you know the input. So transfer function is perhaps is the most important thing, and we'll be using transfer function pretty much in all chapters. Transfer function of a linear system is represented or can be represented by a block diagram, as you can see over here. Input, linear system, which is defined by its transfer function, and the output. Now, many of you, of course, have taken DSP. And if you remember, we did pretty much the same thing in DSP in the digital domain. You have input x of z, and then you have the transfer function h of z in the z domain, and then you have the output y of z. And this is the analog domain. It's not the digital domain, but it's the analog domain, but the concept is the same. Let's do this example based on the RC low pass filter, passive filter that we discussed in circuit analysis. And we have to find the transfer function of this. We did that in circuit analysis, but we're going to do it here again in the Laplace domain. Now, before we do this, let's go ahead and first find out what is the impedance of capacitor and inductor in Laplace domain. How do we represent the capacitor impedance and inductor impedance or reactance in Laplace domain? And those we can figure out using the basic relationship of inductor and capacitor. Inductor capacitor, of course, is the current of the capacitor is given by C dVc over dt. We all know this. And we apply the Laplace transform on this, assuming that the capacitor was completely discharged initially. Then Laplace transform is going to give us IC in the Laplace domain is equal to C, and the Laplace transform of the derivative is from the table. Who remember that? Say it again. S times Vs. S times Vs and then the initial conditions, but we are assuming there is no initial condition. So it's going to be S times Vc S. S by S basically. So if we write this down in terms of impedance, that is V over I, so Vc over Ic, we are going to get 1 over Sc. And this represents the reactance of the capacitor in the Laplace domain, which is similar to if you replace S by j omega, remember. Reactance of capacitor in complex frequency omega domain is 1 over j omega c. And S is basically sigma plus j omega, remember. J omega is part of S. So in the S or Laplace domain, reactance of the capacitor is given by 1 over Sc. And likewise, if you look at the inductor, which is VL is equal to L di over dt. And again, if you apply the Laplace transform, VL in the S domain is L S times, let's say IL in S domain, which gives us VL over S over IL over S to be equal to S times L. And that is the reactance of an inductor in the Laplace domain. Again, replace S by j omega and you find the familiar reactance formula. J omega L is the reactance of inductor here. J omega is basically replaced by S because j omega is part of Laplace domain. Sigma plus j omega, that is S. So anytime you have a circuit in Laplace domain or in time domain and you're converting that circuit in Laplace domain, all the capacitors, all the inductors, you can convert them in by doing S times L as the reactance of the inductor and 1 over S times C as the reactance of a capacitor. And R does not change. R is not dependent on the frequency. So R, it does depend on the frequency, but in general, R does not change. So now that circuit, we have one capacitor. We're going to go ahead and write the reactance of this capacitor, X of C, as 1 over SC. And then, of course, this is your input, V1S in the Laplace domain. This will be IS in the Laplace domain, and this is going to be V2S in the Laplace domain. So let's write down V2 in terms of V1. Who's going to tell me how we're gonna write down V2 in terms of V1? Voltage divider, exactly. So give me the equation. V2S is equal to R plus XC times V1. So the transfer function H of S is simply output over input, which will be XC over R plus XC. And if you're going to go ahead and plug the value of XC, which is 1 over SC, 1 over SC plus R plus 1 over SC. And if you simplify this, then it's going to be 1 divided by 1 over 1 divided by 1 plus S times RC. And that is the expression for the transfer function. Or you can divide numerator and denominator by RC. And you can have in the numerator 1 over RC and denominator S plus 1 over RC, which is better way to write because you don't want any coefficient with the highest power of your S. So a better way to write this is 1 over RC divided by S plus 1 over RC. But in either way, that's the transfer function. Make sense? Good. So any circuit that is given to you, again, you just apply circuit laws on that circuit, and you can always write down in Laplace domain, you can always write down a transfer function for that, and you can always solve that circuit in Laplace in time domain from Laplace domain using the same method that we are using, inverse Laplace transform, partial fraction decomposition, and all those. Yes. Yes. Yeah, they were whole. Laplace actually is a superset because we discussed exponential response of circuit, transient response. We discussed steady state sinusoidal response or steady state response. Laplace combine both. Laplace, when you are solving circuit in the Laplace domain and then going back into the time domain, it shows you the steady state value as well as the transient value. So it combines both things. All right, block diagram models. So a block diagram, as you saw, it defines the transfer function of a system. It shows the input is going in, it shows the block to show the transfer function of the system, and the output is going out of the system. Now, there can be many different type of block diagrams, but you can always reduce a big block diagram into a simple single block, like we saw earlier, a single block with one input and one output if you have a single input and single output system. So there are some rules. If you have multiple blocks in a block diagram, there are some rules as how you can combine different blocks or eliminate blocks such that your system is reduced to just one block. And we're going to look at some of those rules over here. The first thing is, if you have two transfer functions as it is seen here, you have an open loop system, and you have G1S as one of the transfer functions between x2 and x1. G1S is the ratio between x2 and x1, and G2S is the ratio between x3 and x2. If you want to eliminate that and you want to combine both into a single block, then that single block with x1 to be the input and x3 to be the output is simply using chain rules, you can multiply the transfer function of the two blocks together that are in cascade and replace two blocks by a single block, G1s times G2s. Now, since everything is a function of S, Laplace domain, most of the time I don't specify that it's a function of S because it's just become too large. So most of the time you're gonna see I will write G1, G2 instead of G1s and G2s. So in a linear system, if you have multiple transfer functions in series, then you can combine all the transfer function by multiplying them together and replace all the blocks by a single transfer function block with the product of all the transfer function. That's what linear control system, linear systems. So G1, G2 times X3, as I said. Now this slide is small. Let's see if I can make it a little bigger. Anyway, this is from the book. Let's see that. In this, on this slide, basically, in your book, there are 6 different models that are given as how you may have different type of situations in a block diagram and how you can kind of turn one situation into another situation that may be helpful for you when you are simplifying a block diagram. You don't have to memorize all these. Of course, you can use this, your table, you can use the table, but you don't have to memorize all these. Some of them we use very frequently. And those are the ones that if you remember those, they will be helpful, but you can always go back to the table of course. So as you can see, the first one, cascading of blocks, as we just discussed, if you have blocks in series, you can always combine those blocks by multiplying them together, multiplying the transfer functions together. Moving a summing point behind a block, if you have a summing point where two signals are coming and adding or subtracting with each other. And if you want to move this summing point behind a block, then you can do that. You have to multiply the transfer function of the block. You have to multiply with the input, and then you can take the summing point to the output. Why? It's very easy to figure out why they are equal. So just to show you, I'm just going to show you, let's say this one. So in this case, x1 and x2, let's say, they are being subtracted. So over here, let me redraw this. So you have, let's say you have something like this. And a signal is coming here. This is the summing amplifier. And this is negative, which is common practice in control systems to find the error difference of the two signals. So let's say you have x1, or this can be negative or positive, whatever, x2, g, and this is x3. So in this case, if you are trying to figure out what is the value of x3, you're going to come to this point or this signal, and you will see that the signal here is x1 minus x2 because that's coming out of the summing amplifier. So the signal here is x1 minus x2. And if this is plus instead of minus, then the signal is going to be x1 plus x2. Now, when this signal is going to pass through the transfer function, through this control system, the transfer function is going to be multiplied by this signal. So here you're going to get g times x1 minus x2, which is equal to x3 because the signal here is x3. So x3 is equal to g times x1 minus x2. If you look at the equivalent diagram, we are expecting the same x3. So if you look at this right here and apply the same logic. Now the signal, let me redraw this real quick. So now you have G here, and then you have the summing point, summing amplifier, plus, minus, oh, x3. So you have G, and then you have G, x2 and x. And again, if you apply the same logic, at this point you have x1 times G, or G times x1, when x1 will pass through this block. And at this line, you have x2 times G, or G times, write down G times x2 actually. Transfer function times the signal, G times x2. So that's what you have at this point. When they go to the summing amplifier, they're gonna subtract from each other. So here you're gonna have G times x1 minus G times x2. G is common, so G x1 minus x2, which is the same as G x1 minus x2. So again, sometime it might be easier for you to, instead of, if you have this in part of your circuit, part of your block diagram, instead of this, you want to convert into this, and it might be helpful for you to reduce the circuit, simplify the circuit. So you can do that, and that's what it shows in this equivalent diagram, that this can be transformed into that block. So all of them, you can see that, you know, if you want to pick off point ahead of a block, so this pick off point ahead of a block, then you have to multiply this point by G, and likewise you have other block diagrams as well. The one that we use very commonly, we do use this one very frequently. Sometimes we do use this. We use this all the time. We do use this. So there are a few that we use frequently. Some of them we don't really use. Of course, the first one we use all the time. But this is a very good table. You should keep it with you. If you're solving the block diagram, if you're reducing the block diagram, you can consult with this table to see if this table is going to help. And we're going to do problem examples, and we're going to take help from this table as well. Okay, so let's go ahead and reduce this block diagram. This is a very common block diagram that we studied in chapter number 1. You have a controller, you have an actuator, you have a process, and you have the feedback sensor. Transfer function of each is given by those variables: GCS for controller, GAS for actuator, GS for process, and HS for sensor. So we're going to go ahead and reduce this block diagram with a single block, input and the output. Input is RS, output is YS. Now I'm going to show you step by step, and then we can go back and we can see if there's a block diagram that we can use to reduce this. But step by step, sometime it is not. Sometimes you look at the block diagram, it just doesn't make sense to you that how I can use the equivalent block diagram to modify it. Under those conditions, if you're trying to write down transfer function from a block diagram, it's always easy if you just find out the signal at each point. And then finally, you can find out the signal at the output. I'm going to show you what I mean. So start with the first point right over here. EAS is your error signal. So EAS here, what signal is coming here? RS is going in, and this is a summing amplifier. RS is going in, and BS is going in from this side. So this signal is RS minus BS. BS is this signal. Now, what is BS? BS is YS coming into the sensor. Sensor has transfer function of HS. So BS is simply HS times YS. I'm just going to write down HY. So BS is simply HS times YS. So signal at coming out of your summing amplifier is simply R minus HY. And again, everything is function of Laplace domain S. I'm not showing that because it just takes longer. When this signal is going to pass through the controller with the gain GCS, ZS is the output of controller. So what will be ZS? Yeah. So it's going to be GC which is the controller gain, times the signal that is coming in, which is R minus HY. That is going to be the output of the controller. Again, it's going to pass through the actuator with the gain GAS. That's going to be multiplied to produce US, and that's going to be GA GC R minus HY. And finally, this is going to go through the process with the gain GS, and the output is produced, and the output will simply be G times GA GC R minus HY. So that's your output expression. And again, remember, everything is function of S. GCS, GAS, GC, GS, GAS, GCS, RS minus HS, YS. That equation or expression, whatever you want to call it, is the expression for the output of this system, which is YS. So if we want to write down the output expression for this system, YS is equal to GS, GAS, GCS, RS minus HS, YS. Right? Our goal is what? Our goal is to find the transfer function of the system, or first we're going to find the output of the system, and then we can write down output over input to represent the one transfer function of the system, one block. So first write down the output of the system, YS. We have YS here, we have YS here. So I'm going to bring those two YS together, bring this on the left hand side, it's going to become positive because it's a negative sign here. And on my right hand side, the first term is going to be there. YS is common, so I'm going to take that as a common factor. I'm dropping S right now because it's just too many times I'm writing S. 1 plus G, GA, GC, H, and the right hand side is GC, G, GA, GC, R. So the transfer function of this Y over R, which, since I'm already using H of S as one of the variable, I'm just calling it T, transfer function of the system, T of S, is equal to G of S, GA of S, GC of S, 1 plus G of S, GA of S, GC of S, and H of S. So this is the transfer function between the input and the output. And if you want to reduce this block into a single block, then you have the input R of S, you have the output Y of S, and you have the transfer function T of S, which is given by S. So just by following signals at the output of each block, you can easily find the output and the transfer function of even the most complicated block diagram. This is complete, pretty much derivation of your transfer function. Any question about this? Yes. Yeah, T of S, you can see that TS of S is this whole thing. H of S is just the transfer function of the sensor. Yeah. In this case, yes. I'm sorry. This step. So I wrote down the output in terms of the equation that I got right there. And then since there's output on the left-hand side and output on the right-hand side, I combine them together because that's a common factor. And I wrote down y sub s is equal to whatever, this over this times r sub s. Because if you want to find y of t, then you need y of t, y of s on one side and the other things on the other side, right? So I moved this basically on this side. It becomes a denominator. And then if I want to write down the transfer function, complete y over r, then I just bring that r on the left-hand side. So y over r is equal to this over this. And I'm just calling it TS, transfer function of the complete system. Now the same thing, if we go back to the last slide and we see what we can do. First, we can use the first one, combining all the blocks, because you have 3 blocks in cascade. So if we combine all 3 blocks, it's going to be GC, GA, and G, which will be 1 block in the forward path. This is called the forward path. This is called the feedback path. So the forward path is going to be GC, GA, GS, which will be this. And then if you go to the 6th one, you have 1 block in the forward path, 1 block in the feedback path. If you combine these 2, then it's hard to see over here, so small. Let me increase it. So observe, what do we have? X1 is the input, X2 is the output, but your transfer function is G, whatever is the transfer function of this block, G. In our case, it's going to be G, GS, GA, GC, G, divided by 1 minus plus. If you have plus minus here, it's going to become opposite, minus plus. We had negative sign. Our sign in the denominator is positive. But if you have positive sign, so we have positive in the denominator since our sign here was negative. But if you have a positive sign here, then when you do the derivation, this sign is going to be negative right here. And that's what it shows over here. Plus minus is going to become minus plus. So 1, in our case, 1 plus GH. G is, for us, G is GA, GC, G, and H is H. So if you use the first pair and the last pair from this from this block diagram reduction table, then you're going to get the same result that I got without going to that block diagram reduction, just by following different signals. Right? Question? Yes. Yeah. Signals, yeah. It can be amplifier gain. Most of the time it's an amplifier gain, or simply the transfer function of that specific, because one block diagram can represent a huge control system that can have many amplifiers, many other things. So it's not a simple one amplifier. If you have a control system, it can be many things in that control system that are contributing to the transfer function of that control system, including amplifiers. So, but for us, we can just assume the whole thing is acting as an amplifier. And we can assume that, okay, this is the gain of that amplifier. But again, it may or may not be a simple single amplifier. It may be amplified, maybe filters or whatever, right? So everything combined is basically GCS. That's the combined whatever the control system is. The input and output of the ratio between the input and output of the controller block diagram is represented by GCS, and that can be many things inside GCS, that one GCS. So GCS can be given to you in some, we're going to do exercises. GCS can be S plus 1 over S square plus 3S plus 5, let's say. That can be GCS. So that represents that when you solve that controller system, that is your Laplace domain representation of the complete block diagram of the control system coming out to be. Again, that may require you to have 5 capacitors, 3 inductors, whatnot, whatever. So just assuming that this is only a gain of the amplifier may not be a correct assumption, but you can assume it that it is, in general, it is basically the transfer function or gain of the amplifier. You can call it the gain, but don't assume that it's just one amplifier in there and that's producing a gain. It can be a huge system. Some may be producing gain, some may be attenuating the signal, some may be clipping the signal or whatever. So the total transfer function is, because remember, transfer function represent how, again, the response is going to change with respect to the frequency. S is a complex frequency domain. So as S is changing, as the complex frequency is changing, how your signal is changing. And that's what you see in the time domain. When you draw the response in the time domain, you saw that initially, you have this value, and then it's going to increase or decrease, and the final value is going to be this in the time domain. So it's not just, the signal is just multiplied by this gain value, and that's the output. The output is changing every instant of time. And similarly, in the S domain, the complex frequency domain is changing every instant of time based upon at what frequency you're analyzing the signal. I don't know if I answered your question, but you can assume. But bottom line is, if you want to assume that, you can, that okay, this is the gain of the complete system, and that's okay. That's maybe a valid assumption, because you're not going into the system to see how that specific figure is provided or is calculated. You're just looking at that figure. Okay, this is the figure that is given to me. I'm going to use this figure. Assume that to be gain. Assume that whatever. I'm just going to assume that to be a transfer function of the system. That's that is a transfer function of the system. Call it gain. You can call it anything you want. That's fine. It's just a ratio between the output and the input. It could be gain, could be attenuation, could be anything. All right, guys, it's 10:20, so let's go ahead and take a quick break, about 10-minute break, and restart at 10:30. All right, guys, next example. So now we have a little bigger system. Let's go ahead and expand this. This system has multiple loops, as you can see. You have 3 loops, one on top, one is smaller at the bottom, and one bigger around the system. And again, we have to reduce everything in a single block diagram and write the transfer function between the input and the output. We're going to get help from our block diagram model. And the first thing that we can see, now when you have a multiple loop diagram, generally you start reducing the innermost loop first and then expand. Innermost, then the one that is bigger than that, and then in this case, the biggest of all. So the first one, what we're going to do, we cannot do this right now because you have a pick-off point right over there. So what we are going to do first, we are going to move this point behind G4. And then we are going to simplify this, the smaller loop. Once we simplify this, the smaller one, replace it by a single block, then we can simplify the bigger one, the one on the top. And then once we simplify that, then we're going to come back to the biggest one, which is at the bottom. So that's the plan to solve this block diagram. So first, we're going to move this point behind G4. So if we go here, and if we look what exactly we are doing, so we have a pick-off point, and we are moving behind. So let's say this point, we are moving behind a block. Then we have to multiply by 1 over G in the feedback block. So if you're moving this point behind G4, in the feedback loop, we're going to multiply by the gain 1 over G4. So again, we are using point number, number 4 over here, moving a pick-off point behind a block. So you multiply by the gain 1 over G4 in the feedback loop. So let's do that. I'm going to move it here. May have to redraw this, but it's not going to look good. I don't want to redraw this too much. So, but let's go ahead and redraw this. This, and then we have another block. This block, then we have this, we have another block. And then we have another 1, 2, 3. We have the third summing amplifier. And then we have one block, and then we have another block. And this is the output. Signal is going from here to here. And then we are going to move the pickoff point that was here behind this block. So we have this. We're going to introduce 1 over G4 over here. Okay. This is your block diagram. So this is your R of S plus minus H3 of S G1S, H3 of S G1S, G2S, G3S, G4S, G2S, G3S, G4S, and then I have H2S, H1S, this is H1S, and this is H2S, and this is going to be 1 over G4S, G4. So again, we moved the point that was here. H2S was coming here. We moved that pickoff point behind the G4S block, and we introduced 1 over G4S in the feedback. Yes. Is it? Let me see. H2 is going to the first one. Okay, so I'm going to move this here, and then I'm going to move, I'm putting it here. So I'm going to move this here. So let's go ahead and move this. Let's go ahead and move this over here. And all right, so what is the summation is negative and positive, negative and positive. And then for this one, I have positive and positive, positive and positive. Okay. All right, so then now we're gonna solve the smallest one, the inner one, which is G3S, G4S, and H1S. We're gonna solve that first, and then we're gonna solve whatever is the resultant. We're gonna solve the top one and then the bottom. So when we eliminate this one, we are going to use number 6 or the one that we did over here. Basically, it's a similar one. And the result is going to be G, basically the combined transfer function in the numerator divided by 1 plus combined transfer function in the numerator times the transfer function of the feedback. So it's going to be G3, G4 divided by 1 minus, since we have a plus sign over here, that's going to be minus 1 minus G3, G4 over H1. G3, G4 over 1 minus G3, G4, H. That's going to be the combined block to eliminate this whole thing. So and then this whole thing is going to be eliminated. Let's call this T1. So this is T1S. G3, G4 over 1 minus G3, G4, H1. RS plus minus H3, G1 plus minus H2, 1 over G2. And then this thing is G2 right here. Oh, this is 1 over G4, not G2. Let me make it a little bigger. One over G. G2 and then T1. T1 is this, which is represented by G3, G4 over 1 minus G3, G4. And that's your surface. So T1 is G3, G4 over 1 minus G3, G4, H. So start with the elimination of the innermost one. And I eliminated that innermost one and replaced that by T1. And now we can go ahead and eliminate the one that is bigger, which is this one. Replace it by a single block. When we replace it by a single block, let's say T2. T2 will be equal to G2 T1, which is in the feed forward loop, and then 1 plus G2 T1 times the feedback loop H2 divided by G. G2 T1 divided by 1 plus G2 T1 times H2 times 1 over G4. If you have any question at any point, please ask. Yes. Mm-hmm. So you're talking about this negative? Because both signals are adding. The one that are going in the summing amplifier over there, both are adding. So if the feedback signal is adding instead of being subtracted, then in the denominator you're going to have negative. So you're going to have the opposite sign. If you look at, again, if we go back and look at that block diagram again that we are using, so we are using the last block diagram. We are using 6, eliminating a feedback loop. So observe, you have plus minus over here. You can have a positive or negative in the feedback. If you have plus minus, then it changes its sign. In the numerator. It becomes negative positive. So if you have a plus sign, it's going to become negative. If you have a negative sign, it's going to become positive when you do the derivation. Yeah. Okay, so let's go ahead on the next slide. I'm gonna go ahead and eliminate that and put T2 in place of the whole thing. So I'll have G1, T2, and then H3, 3 things. Oops. G1, T2, and H3. And again, T2 is G2 T1 over 1 plus G2 T1 H2 G4. G2 T1 over 1 plus G2 T1 H3 over H2 over G4. H2, not H3. That's our T2. And now we have a single loop. So we're going to go ahead and combine everything in one block. And let's call this the final transfer function, which is T of S, Rs, Ys. And T of S, of course, will be equal to G1 T2 over 1 plus G1 T2 H3. So this is the final transfer function. Of course, in T2, we know already what T2 is. We're going to plug that in. We already know what T1 is. We can plug that in and then have a simplified version. We're not doing the simplification right now, but eventually, if you have to figure out one transfer function in terms of a numerator over denominator, a polynomial of S divided by polynomial of S, you're going to go ahead and plug in T2. You're going to go ahead and plug in T1 and then write down the final transfer function of T of S. So in this case, we are using two relationship from that block diagram module. One pickoff point moving beyond a block, and then elimination of the feedback loop. 3 feedback loops we eliminated in this case. Question. Again, the feedback loop, make sure do not make the mistake of positive and negative, because I have seen that mistake. Students make it usually. If the feedback loop is coming and it is being subtracted from the incoming signal, then in the denominator you're going to have positive. And if the feedback loop is coming and adding into the incoming signal, then you're going to have a negative in the denominator. So that I have seen that mistake students make quite often. So please do not make that mistake. Yes. Here you can make a negative. I don't know. I have not seen negative. The incoming signal is the incoming. Well, if it's again, if you have an inverting amplifier, that's a different story, right? But you can still call that signal as RS, whether it's a negative signal or positive signal. That is still an RS signal. So that's your input. Now, the signal that is coming in, you are subtracting, most of the time, you're subtracting that input to find what is the error. So most of the time, it's being subtracted. The incoming signal is subtracted from the input signal generally. Yes, question? There was a question. Yeah, we did that positive, positive. You can have two signals being added together right here. They were positive, positive right here. So when we added them together at the denominator, we have the negative sign. So you can have two signals being added together. Remember, positive still means if the signal value itself is negative, then if you're adding it, still you're subtracting it in general, right? Yeah, go ahead. So you have two feed forward loops. You cannot eliminate that. You'll have to take the signal from the straight loop, and then you have to go and jump from the other loop. We're going to discuss that under the signal flow graphs. But remember, feed forward, and again, that's a good question, because I have seen that mistake as well. If you have two feed forward loops, make sure do not eliminate the feed forward loop using the feedback loop formula. That is not applied on feed forward loop. Feed forward means that you have a straight path, and then instead of coming back, that thing is also going towards ys instead of coming back from ys. So that's the forward, not feed forward, sorry, that's the forward loop. So now you have two forward loops instead of a feedback loop. You're going to have two forward loops. You cannot eliminate the forward loop using what we are doing here. That's not applied on the forward loop. Then you can do what we did earlier. If you want to find out, you can basically apply the signal at each point, and then you can easily find out what is the output in terms of both forward loops as they combine together, what will be the output. But do not use the feedback loop formula to do that. I've seen that mistake. Yes. It's a bigger block diagram, so it is going to be more complicated. Yeah, the bigger the diagram is going to be, and if you follow each signal, then so if you're following this, the main idea is to write the output in terms of basically this equation. So you have to go to the output, final output. When you're doing that, then the bigger the diagram is going to become, the more complicated that equation is going to achieve that you're writing. If you simplify the block diagram first and then achieve that equation, then it becomes simpler in general. But you can do that though. It's not like you cannot do that. You can still do that. Yeah, there's always going to be one equation. So you can still do that, but again, you'll have to go through multiple steps to find that bigger equation at the output, which will be equal to the output. So in this case, it was a single loop, so it's pretty straightforward. The output is equal to that equation. But if you have multiple loops and all those things, it becomes a little complicated, basically. But you can do that. It's not like you cannot. You can always do that. You can always follow the signal and write the equation in terms of other signals and other gains. All right, so let me delete this. All right, what is this? Determine the output ys of s due to two inputs in the following transfer function. Rs is the desired output, and TDS is the external disturbance. Okay, so in this case, this is a very common case of a control system that you have external disturbances. As we discussed last time, you can have external disturbance as well as you can have internal noise. Right now, we don't have any internal noise in the signal that is given to us, only the external disturbance. In this case, when you are writing the transfer function, or not transfer function, when you're writing the output of the system, you use superposition. That is, you keep only one input active at one time, and based on that input, you write the output. And then you're gonna combine all the outputs together, which is because of RS, what is the output, and because of TDS, what is the output. Once you have those, you're going to combine them together, and that will be your final output. So determine the output voice of S due to the two signals. One is our desired output. RS is our desired output. This is what we want to see as YS. And TDS is the disturbance in the signal. External disturbance can be electromagnetic waves, can be wind, can be anything that is affecting your system. So we're going to use superposition. Use superposition. Let RS be active and TDS be inactive. So basically, we will assume that TDS is 0 right now. So when you do that, basically you eliminate TDS, and this becomes simply a single loop circuit, single loop block diagram. And for that, we know that the output voice of S will be equal to G1S G2S over 1 plus G1S G2S HS times R sub S. And this is basically based upon this, what we did earlier. G1S, G2S, in this case we have 3, so 3 of them plus 1 plus that times H of S. Because when you eliminate TDS, TDS is equal to 0, then there is nothing that is added basically here. So this summing amplifier is just going to be eliminated because you're not really adding two signals here. One is 0, the other signal is coming in. So the output will be only the signal that is coming in. Yes. No. Again, I did not do the derivation again because we already did that. But if you want to do the derivation again, you can go back, or you can just look at the last pair. We are using the last pair again. Yeah. Why we multiplied it? Because it is going to be, let's go back here then, right over here. So it is going to be Y is equal to this whole thing times R, right? Y is equal to this over this. So R is being multiplied by, remember, again, go back a little further maybe when we discuss right here, block diagram, X1, X3. So if you are trying to figure out X3, or trying to figure out right here, Ys is equal to Hs times X of S. That's the transfer function. So the transfer function is multiplied by the input to produce the output in the S domain. And that's what we see over here. This is the transfer function between Ys and Rs. Because if you eliminate this whole thing is going to be replaced by this. So that's one block between Rs and Ys. So Ys will be equal to Rs times that block, right? Okay, next we're gonna keep TDS active and make Rs inactive. Now let TDS be active and Rs be inactive. Let's use another color. So let's say Rs is 0 now and TDS is no longer 0. Now, in this case, I'm going to follow the signals again. So Ys times Hs. So the signal here is Hy. Hs times Ys. The signal here is going to be 0 minus Hy. Simply negative H times 1. It's going to pass through G1. The signal here will be negative G1 Hy. That will be added into TDS. So the signal here is negative G1 HY plus TD. And that will pass through G2. So the signal here is going to be G2 times TD minus G1 HY times Y. Not Y, sorry, is equal to Y. Is equal to Y sub S. So we're going to take that expression and then we're going to write down Ys in terms of TD. See if you have any question about that before we write down the expression. Yes. We can also what now? We don't have to do that. I mean, if you want, you can, but you don't have to do that. I mean, I'm just following the signal basically. That's all I'm doing because it's a single loop. It's pretty straightforward. Now remember, RS is not there, so you can kind of rearrange this. You can shuffle the diagram such that your TD become your the only input because you have only one input TD. RS is not there; it's 0. You can remove RS, and TD is your only input. The shape of the block diagram is different because we usually have our input signal on the left side. In that case, input is coming on top instead of left side. But you can create a topology such that TD is moved on the left and you still have one loop. It still has one loop basically, right? The first summing point is basically 0 minus HY. So it's just the signal is being subtracted that is going. So it's acting as an inverting amplifier simply. R is not there, but this amplifier becomes an inverting amplifier. Take HY signal and invert it basically, shift the phase 180 degrees. So that summing amplifier becomes pretty much inverting amplifier. Summing amplifier is an inverting amplifier. The nature of summing amplifier is an invert. So when did you take integrated circuits yet or no? Regular was the class. I know you might have taken integrated circuit sometime, but the class. So if you remember the summing amplifier, the output of summing amplifier is 180 degrees out of phase with the input signals that are coming in. So basically, the summing amplifier is acting as an inverting amplifier anyways. If you want to make it in phase, then you put an inverting amplifier at the output of a summing amplifier to make the input and output phase to be the same usually. But in that case, as I said, just consider that summing amplifier that two signals are coming in, one signal is 0, the other coming in is a negative signal. So the output is just going to be a negative value because that's being subtracted from the input. So whatever you want to assume it to be. I'm just following signal at each point, as I said, to write down my equation, which is, and I can call this as Y1 because I'm going to call this Y2. So Y2S is equal to G2S TDS minus G1S HS and Y2S. And from that, I can bring the term with Y2 on the left side and combine it with this because it's a common factor. So I'm going to get 1 plus G1S HS. When I bring this term and G2S, sorry, G2S is outside multiplying everything. G1S, G2S, HS. And on the right hand side, I have G2S, TDS. So my output in terms of TDS, I can write down Y2S equals G2S over 1 plus G1S G2S HS times. So now I have y1 and y2. And since we are applying superposition, we're going to go ahead and find value of y by combining both y1 and y2 together, applying the superposition principle, and have our final output as the sum of both transfer functions. So y of s is equal to y1 of s plus y2. What did we have? G1, G2, H. G1s, G2s over. That's a complete transfer function of your control system when two signals are present, input signal and the disturbance signal. All right, guys, any question about this? Yeah. If you have a third input, which we will have error signal, internal error to the system, which will be here, then you're going to do the same thing. You're going to deactivate RS and TDS and keep only the error signal active. And then you will write down YS in terms of the error signal. That's going to be the third input. So your the YS complete YS expression is going to be three parts due to RS, due to TDS, and due to ES. Yes. Yeah, to find the output only because of the disturbance, you will assume that you will just turn the input off and then see what is the output because of that disturbance. Yeah. You have to have some input if you want to see what is the effect of input plus disturbance. Then you're gonna bring the input back in the system and then see overall output that is because of the input and because of the disturbance. Yeah. So the input usually does not affect the disturbance because it's outside the system. Yeah. You mean how y become y2? Oh, just using y2 for the TD and y1 for when I have RS in the circuit. Like in superposition, if you're solving for voltage in a circuit, let's say. So if you have two sources, you say, okay, because of this source, my voltage is V1. Because of this source, my voltage is V2, and then you add both of them together. I'm using the same thing. Basically, I'm saying if you have only R in the circuit in the system, then the output I'm gonna assign a variable Y1 because of R. And if I have only TD, then my output I'm gonna assign a variable Y2. So Y2 is only because of TD, Y1 is only because of R. And the complete output is going to be the sum of both Y1 plus Y2. That is both because of R and TD. If there's a confusion, if there's something else, then I can answer that. No, I mean, yeah. So that's the same equation that I'm writing over here. Instead of Y, I'm just assigning a variable Y2 because that equation is because of TD as input. So right here, this, because you have a Y, G1HY at the end. So that's Y is Y2 basically because it's because of the TD. Yeah. Yeah. Okay, guys. So let's see. So this is the final transfer function. This slide is deleted. Next topic is, so after block diagram, we will see how we can represent systems using signal flow graph. Sometimes it's easier to represent system as signal flow graph, and it's easier to write down the transfer function, especially if your block diagram is too large. If you can put that in signal flow graph, then there's a formula that you can use, which is called Mason's gain formula, and that might be easy for you to write down the the transfer function of the system using Mason's gain formula. So when you're converting a block diagram into a signal flow graph, as you can see in this diagram, in this figure 2.10, anytime you have an input, that becomes a node in the signal flow graph. So you have R. Basically, anytime you have a signal, not input, sorry. Anytime you have a signal, that can be represented as a node in the signal flow graph. So you have a signal R, you have a signal E, you have a signal C, you have a signal B. So all of these are represented as different nodes. And the gain of each block, they become weight of each signal. So you have a gain 1 because there is no gain, so that's just represented by 1. And then you have E, and E signal, of course, is R minus B. So the E node is R is coming in, R times 1, R. And then you have a B node, so B times -1, negative B. So E node is R times negative B, which is E. And then E passes through G to produce C. So E passes through the gain G, G times E, and that is going to produce C. And then B is C times H. So the weight of this line is H. So C times H is going to produce the signal B. So each signal is going to be represented as a node, and the gain of, or the transfer function of each block is going to be represented as the weight of each line. And then you have the branches, as you can see, to represent the gain. So every block diagram can be represented in a signal flow graph. And once you have signal flow graph, then we can apply Mason's gain formula to write down the transfer function. There are some, of course, node, as I said, node signal represent your input or output points, or basically signals, basically. A branch represent a unidirectional path segment that carries a weight or a path gain, similar to the transfer function. A path represent a single branch or continuation of branches from one node to another node. A loop represent a closed path that starts and ends at the same node, and with no node is repeated twice along the path. And then you have non-touching loops, that if you have loops that are not sharing any node or any branch, then those are the non-touching loops. And then, of course, touching loops are going to be that are sharing branches or sharing nodes. Mason's gain formula is given by this equation. The transfer function of a block diagram from signal flow graph is given by the sum of all the forward paths. So these are the forward paths. K is the forward path. If you have n forward paths, then you are summing up all the forward paths. Pk is your transfer function of each forward path. That's Pk, gain of the kth forward path. Delta K, well, let's do delta. Delta is the determinant, what we call determinant. So how do you calculate delta? Delta is equal to 1 minus sum of individual loop gains. So if you have, right now you have only one loop, and the gain of this loop is G times H times -1. The product of each, weight of each branch is the gain. So that loop, your gain is G times H times -1. You have only one loop over. So this delta, 1 minus sum of individual loop gains. So if you have one loop, then of course it's just going to be that loop gain, plus sum of gain products of all combination of two non-touching loops. If you have non-touching loops, then you are going to take the product of each of the non-touching loop gain, and then you're gonna add them together. And that's what it means over here. Sum of gain products of all combinations of two non-touching loops, minus sum of gain products of all combination of three non-touching loops. Usually we don't really go up to 3. In some problems, you have, most of the problems you have 1 and minus sum of individual loop gains. Because most of the time your loops are touching with each other, as you will see. But in some problems, there may be that two loops are not touching with each other. In that case, you have to go to this as well. Sum of the gain product of all combination of two non-touching loops. We never really go to the third one, this one, because there's, I have not seen the occasion, at least in this class, that you have 3 non-touching loops. There are some that you have 2 non-touching loops, but not the 3 non-touching loops. So that's the denominator delta, which is what we call determinant. And then the numerator delta K is the part of delta not touching the kth forward path. So any part of delta which is not touching the kth forward path is delta K. When we do the problems, you will understand how to implement this, because just explaining this is a little difficult. So if let's go and do this problem. Determine the transfer function of the following control system. So signal flow graph is given to us for this control system, and we have to find the transfer function. Now, earlier, who asked me, I think you asked me about the forward, if it is going forward. Now observe, in this case, you have one forward path going from R to C straight up, and then you have another path going from R and then taking this route and then going to C. So in this case, you have 2 forward paths. That's the question that you asked me earlier, right? So in this case, if this thing is given as a block diagram, if I convert this thing into a block diagram, then it is going to be something like this. You know, you have R, then you have a summation point, and then you have a G1 over here, and then you have another G2 over here. This is the forward loop, this is the forward loop, G4. So in this case, again, this becomes the forward path, and you cannot eliminate this forward path using the feedback path. Okay, coming back to this. So we have to write the transfer function of this. Using Mason's gain formula, the transfer function, let's say T of S is K is equal to 1, and we have 2 forward path. So it's going to be 2 forward path. P of K, delta of K over delta. So K again is the forward path, number of forward paths. One is going directly straight from R to C, and other is going R through G4 and C. So first, our P1 for the first path, the straight path. What is the gain of P1 that is going straight? You multiply all the gains, all the branch weights. So 1 times G1 times G2 times 1 times 1. The path that is going from R towards C is straight. That's our first path. So you multiply all the weight branches, G1 and G2. Rest of them are 1. So P1 is simply G1 and G2. And then the second forward path, which is going from R through to node 1, G4, node 4, and then C. So 1 times G4 times 1. So simply G4. Gain of the second forward path is simply G4. Let's look at delta. 1 minus sum of individual loop gains. Okay, how many loops do we have now? So we have, of course, this loop right here. We have this loop right here. And anybody see another loop? We have this loop right here, outer loop. So we have 3 loops in this signal flow graph. Loop, of course, is a closed path that starts at the same node and ends at the same node. That's a loop. So you have inner loop, you have an outer loop, and then you have the loop around G4 and G3, that is, or G4 and G5. So 1 minus, let's go with the, we can call this loop 1, let's say. So this is loop 1, this is loop 2, and this is loop 3. So 1 minus loop 1 plus loop 2 plus loop 3. Gain of loop 1, 1 minus sum of individual loop gains. So 1 minus the gain of loop 1, which is going to be G2 times G3. G2 times G3. This is loop 1. Plus loop 2 is G1, G2, 1, and it's negative G5, I believe. Let me delete this. Yes, negative G5. So let me write this down. 3 loops and 2 forward paths. So loop 2 is G1 times G2 times 1 times negative G5. So that's the loop bottom. G1, G2, G1, G2, and negative G5. Negative G5. And then the loop 3, which is the outer loop, circular loop, which is G4 and negative G5. So plus G4 and negative G5. Yes. Yeah, a loop has to start and end at the same node. That's a loop. So these are the product of sorry, this is the sum of all the loop gains, L1, L2, and L3. This is L2 and this is L3. All right. Now, do you see any loops that are not touching with each other? That is, loops that are not sharing any node or any branch. Are there any loops? L1 and L3, definitely. L1 and L3, they are not sharing any node, nor they're sharing any branch. Of course, L2 and L1, they are sharing nodes. L2 is this. And likewise, L2 and L3, they are sharing nodes and branches, but L1 and L3, they're not. So that's the third part of this. That is, sum of gain products of all combination of two non-touching loops. So there are only two non-touching loops. So we're going to put plus L1 times L3, which is going to be L1 is, this is L1. So G2 times G3. And L3 is G2 times negative G5. And this is, let me write it down, this is L1 and this is L3. Let's write this down here. L1 and L3 are non-touching loops. So sum of gain products of all combination of two non-touching loops. Sum of gain products. So those are the gain products. And since you don't have any other loops that are non-touching, basically that's the only one that we have. So if you have some more loops that are non-touching, then you're going to take the gain product of those, and then you're going to add it in this. But this is the only, these two are the only one. So there's a product of the two non-touching loops, which is right here, product of two non-touching loops. And since there is no other non-touching loops, so we cannot create a sum. It's only these are the product of the two non-touching loops. If you have another L4 or something, and that's also non-touching with L3, then you're going to do L3 times L4, and then you're going to add that into this L1 and L3. Yeah, combination. Yeah. Mm-hmm. And now we're going to look at, so this is delta. There are no three non-touching loops, of course, so we are not going to progress further. This is the, basically, as I said, this is pretty much the farthest that we go. Usually we don't really have this actually. This is a specific example that I took just to explain that in this case, you do have non-touching loops. And you have more than one path as well. Now delta K is delta, and then you remove all the loops that are touching the kth path. So basically, the gain of all the loops that are touching the kth path. That's delta K. So delta 1 in this case is corresponding to the straight path, and all the loops are touching the straight path. They're sharing nodes when you go from R to C. So basically, delta 1 is simply going to be 1 because L1, L2, L3, all of them are touching your straight path. Now, what about delta 2? Delta 2, you're going from R, G4, and C. Now, you have a common node, which is with loop 2, but you are not touching loop 1 if you go from R through loop 3 through G4 to C. So L1 is the only one that is non-touching, that is not touching the path from R to C through G4. So that has to be included in delta 2. So delta 1 is 1, and delta 2 is 1 minus only L1 is not touching the second path from R to C. So 1 minus the gain of L1, G2 and G3. Not touching the second straight path. The second path, not straight. The second forward path. Not touching the second forward path. Which is L1. This is L1. So now we have everything, and we're going to write down the transfer function. T of S is equal to P1 times delta 1 over delta. So P1 is G1 G2. P1 delta 1 plus P2 delta 2 over delta. P1 is G1 G2 and delta 1 is 1. And P2 is G4 and delta 2 is 1 minus G2 G3. And delta is 1 minus this plus this. I don't want to write all those things. One minus G1 G2 plus G1 G2 G5 plus G4 G5. 1 minus G1 G2 plus G1 G2 G5 plus G4 G5. And plus or minus G2 G3 G2 square G3 G5 minus G2 square, and that is going to be the transfer function of your system. So once again, signal flow graphs are used if the system is kind of complicated, and if you identify correctly how many forward paths are there, how many feedback loops are there, then using Mason's gain formula, you can kind of relatively easily you can write the transfer function instead of going and combining blocks and all those. Because that system is pretty complicated with 2 forward loops and all those 3 feedback loops and all those things. So if you're solving this thing into using a block diagram, then it's going to take pretty long to solve this thing. But with the signal flow graph, it's much easier to write down the transfer function without even any reduction of block diagram or anything. You just have to identify correctly which are the forward loop, which are the feedback loops and all those things, which are the non-touching loops and all that. G2, G3. L1 is G2, L2 is G1, G5. This is G1. That's not G2. This is G1. L3 is, no, L2, sorry. No, L3. L2 is what? L1, L3. L3 is G4 negative G5. And then L1 is G1, G2, G3. No, that's fine. I don't know what it is. G4, this is G4, L G4 and negative G5. Let me go fix that. G2, G3, G4, G5. G2, G3, G4. All right, guys, any question about this? Okay, let's go ahead and take another short break, about 8 minutes, and start back at 11:45. Let's go and do this. This is also signal flow graph, so we're going to do this, and then most likely we will have some time to start chapter number 4 and do a little bit of chapter number 4 today. Finish chapter number 2 and then do a little bit of chapter number 4. So let's start in about 6-7 minutes. All right, guys, this is the last example of this chapter. And in this case, we are given a circuit. It's another low pass filter basically, and they're asking us to draw the signal flow graph of this low pass filter. And then from the signal flow graph, we're going to calculate the overall gain, which is V3 over V1. That's the overall gain. So first thing we're going to do, we are going to write down the equations to draw the signal flow graph. We have certain signals, V1, I1, V2, I2, V3. All of these are signals. And then we have gains, of course, R, and X of C, of course, or C. So this is going to be in the Laplace domain. It's going to be X of C, which is 1 over SC. I'm just going to write down X of C right now. First, we're going to write down the equation for I1. So I1 is going to be what? Yes. So V1 minus V2 divided by R. And we can write this down as V1. And 1 over R is the R is not a function of that. 1 over R is the conductance. So I'm just going to write down in terms of conductance. G is equal to 1 over R. All right. The next signal is I2S. And I2S similarly is the voltage V2S minus the voltage V3S over R. V2S minus V3S times G. Yes. G is conductance. It's not transconductance. 1 over R is conductance, which is G. Transconductance is usually we take it in the transistors. This is simply a conductance, which is 1 over R. All right. Next signal that we have is V2S. V1 is our input signal, of course. So V2S and V2S when we write down. So I1 is coming in, I2 is going out, and V2 is this current. let's call this, I don't know, what do you want to call it? Since we have I1 and I2 already, I can call it I3. So I3S times R is V2S. And what is I3? I1 is equal to I3 plus I2. So I3 is equal to I1 minus I2. Because our signals are I1 and I2, so I'm going to write this down in terms of the signals that we have. I1S minus I2S times. And finally, our last signal is the output, which is V3S, which is equal to simply I2 is going through capacitor, and the voltage across the capacitor is V3. So I2S times X. So now we have all the signals, all the nodes. Our nodes are, of course, V1, I1, V2, I2, and V3. Those are signals. So those are our nodes. And then we have also gains of each branch. We have G, we have R, and we have Xs. So let's go ahead and draw let's see if I can use this space to draw it. It's a smaller space too. So we're going to start with, let's use another color. We're going to start with the input, which is V1. V1S, that's our input. And my next signal is I1. So that's another node, I1S. My next signal is V2. That's another node, my V2S. My next signal is I2. I2S. And my final signal is V3. So these are my 5 nodes that represent signals. Okay, I1S from the first one, I1S is V1S times G. So we have V1S, and I'm going to make the gain of this to be G. So V1S times G is going to be part of I1S, and then negative V2S times G. So I'm going to bring a loop, and should not put a not put an arrow over here. Arrow is going to represent the gain of the branch. So I'm just going to connect this without arrow, and the gain of the branch is represented by the arrow, which is going to be negative V2G. So that's going to be negative G. So your I1 is going to be V1G plus V2 times negative G. So V1G minus V2G, which is V1G minus V2G. Make sense? Any question? Okay. So we're going to move on. Now I have, so my V2 is I3R, which is I1S minus I2S times R. So this is my V2, and V2 is I1S, so I1 is here, times R. So this is going to be R, I1S times R, and then minus I2 times I2S times R. So I'm going to create another feedback loop over here. I'm going to move it from here to here, and the gain of this is going to be negative R. So V2 is I1 times R and I2 times negative R, which will represent this equation. I1 times R minus I2 times R. My I2 is V2 times G minus V3 times G. So V2 is this, V2 times G minus V3 times G. So I'm gonna create another feedback here. No, not. And the gain of this is going to be negative G. I can extend this a little bit and show V3 S and then just give a gain here 1. So that's my I2. I2 is V2 times G minus V3 times G. V2 times G minus V3 times G. And finally, my V3 is I2 times X of C. So my V3, which is right over here, is I2 times X of C. So I2 is here, and this is going to be X of C. And that's my V3. Let me know if you have questions. So that circuit represented in terms of signal flow graph is going to look like this using these equations, of course. Yes. Yes, that's what we're doing. Yep. That's why it's important to write the equation first before you draw the signal flow graph. So now we have signal flow graph, and now we can apply Mason's gain formula on this signal on this signal flow graph to get V3 over V1, the total transfer function of this circuit. Of course, we can solve the circuit and find it. The circuit solution is easy, of course. But let's go ahead and do that. So how many forward paths we have? We have only one forward path from V1 to V3. Only one forward path. We have 3 feedback loops, and we have 2 loops that are not touching, which is this loop and this loop. They're non-touching loops. Of course, this loop is touching both this and this. So let me put L1, loop 1, L2, and L3. So these are our 3 loops. So we have 2 non-touching loops, L1 and L3. Like in the last problem, we had the 2 non-touching loops. And one forward path only. So using Mason's gain formula, transfer function, which is going to be V3 over V1, V3S over V1S, is given by K is equal to 1. And since there is only one forward path, so it's just going to be 1 to 1, Pk delta K over delta. So going back, P1 is the gain of the forward path. So the gain of the forward path is G times R times G times X of C. Weight of each branch multiplied by each other. G square R X of C. Now R and G are reciprocal of each other. So I'm just going to go ahead and cancel these, R times G. So that's going to be simply G times X of C. That's the gain of my forward path. My determinant delta is equal to 1 minus sum of all loop gains. So I have L1, L2, and L3. So let me write this down first. L1 plus L2 plus L3, gain of each loop, plus product of sum of product of two non-touching loops. So in this case, we have only these two loops that are non-touching, L1 and L3, plus L1 and that's going to give us 1 minus L1 is R times negative G. So minus minus plus, so I'm going to write down R times G. L2 is again G times negative R. So plus G times negative R, and L3 is negative G times XC. So again plus G times XC. And L1, L3 is going to be R1 times G times XC. R1 times G times XC. And again, G and R are reciprocal of each other. So I'm going to go ahead and put 1 for those. 1 plus 1 plus 1 plus G of XC, G times XC plus R times G is one. Why I'm putting R1? It's not R1, it's just R. R times G is 1, so G times XC. So this will give us 3 plus 2 G times X of CS. That's my determinant, denominator. As far as delta 1 is concerned, all the loops are touching the forward path. So the only thing that will be left is 1, because L1, L2, L3, all of them are touching the forward path. So delta 1 is equal to 1 since all loops are touching the forward path. So now Mason's-Grain formula, through Mason's-Grain formula, it's very easy. I'm just going to write down here. I'm not going to go into the next slide. So this is going to be P1, which is G times XC divided times 1 divided by 3 plus 2 G times XC. And that is the transfer function of this system. Now you can plug in XC is equal to 1 over SC and further simplify this. And G you can do 1 over R if you want. So if I want to further further simplify it, then I can write down G over SC, or instead of G, if I want to do R, since R is part of your given circuit, then 1 over SCR, since G is 1 over R, divided by 3 plus 2, 2 over SCR. Again, XC is 1 over SC and G is 1 over R. So your further simplification is going to give you 1 over 2 plus 2 plus 3 SCR. So 3 RC times C. So now you have everything that is given in the circuit. R is given in the circuit, C is given in the circuit. And that will be the transfer function of the circuit. All right, guys, any question about this? Good. So once again, generally, signal flow graph, if you read it correctly, then it's rather easier to get the transfer function from a signal flow graph, even for a very complicated block diagram. All right, any other question about this? Okay, so this concludes chapter number 2. Of course, there will be homework that I'm going to post from chapter number, rest of the topics from chapter number 2, and then quiz is going to be next week. Now we have half an hour, so we're going to start chapter number 3 and then do it. I'm going to stop the recording so that I can just post chapter 2 separately and chapter